Okay, in this section we're talking about concavity, and concavity is the shape of the curve. If it's concave up, I think of it as if it would hold water, and if it's concave down, it would let water out. So you see a little definition there that you can read, but the most important thing about concavity is that it's the second derivative. Okay, it's the second derivative. Increasing and decreasing is the first derivative, but concavity is the second derivative. So basically you're doing the same thing you did in the previous section, except you're doing it all with the second derivative. The functions are a lot easier too. Okay, so in this one I ask you to determine the intervals of concavity and find the inflection points. So on your guidelines that I give you on the previous page, it says find the domain. Okay, so that's easy to do here. It's a basic polynomial, so my domain would just be all real numbers. And I'll go ahead and mark that on my number line. Okay, step 2, determine where the second derivative equals 0 or where it's undefined. Okay, be careful here, it's the second. In a multiple choice format, for those of you taking a multiple choice class, I'll trick you every time by giving you the answers for the first derivative. This is not the first derivative, it's the second. So taking the first derivative to get started, we would have 3x squared minus 6x minus 24. Okay, that's not enough. So we take our second derivative, and so we get 6x minus 6. Okay, this is the derivative that we will use. Find where that derivative equals 0. Let me fix that. Or where it does not exist. Okay, it only does not exist if there's a denominator, which there's not. So you take 6x minus 6, that's your second derivative, and set it to 0. So we're going to put x equals 1 on our number line. You're going to choose a test point from each interval. A number I might choose out here, I might choose 0. A number I might choose out here, I might choose 2. Now what you're doing with these numbers, plug these test points into the second derivative. Okay, so my second derivative here is 6x minus 6. If I plug 0 into that, I get negative 6. Negative is what's important. If I plug 2 into the second derivative, I get 12 minus 6, which is a positive 6. Now this is not increasing, decreasing, so don't draw arrows, but it does tell you a lot about the graph. So this first one you'll notice it's negative. That means it's concave down. The second one you notice is positive. That means it's concave up. So this particular graph is concave up from 1 to infinity. It's concave down from negative infinity to 1. Now, going back to your directions, your guidelines, underneath your guidelines rather, it says inflection point. An inflection point is a point on the graph where the concavity changes from upward to downward or downward to upward. If you have any change at all in concavity, that's an inflection point. So you'll see the value 1 here. On the left side it's down, and on the right side it's up. Since there's a change there, that means you have an inflection point at 1. Now, to find the y value, here we go again. Use the original function. Now there are several functions to the left of the screen. Make sure that you use the original. So your original function is x cubed minus 3x squared minus 24x plus 32. I'm going to plug in the number 1. 1 cubed minus 3 times 1 squared minus 24 times 1 plus 32. So we'd have 33 minus 27. Is that 6? So my inflection point, the only one I'd have, would be at the point 1, 6. Okay, let's go ahead and knock out the second one. I asked you to determine the intervals of concavity and inflection points for this particular one. It is a polynomial, so your domain is all real numbers. We'll go ahead and put that on our number line. I know that concavity is my second derivative. So we have to start somewhere, so we'll start with the first. Okay, then we'll take the second derivative. Great. So we'll take that second derivative and set it to 0. I know I'm going to have two answers because it's an x squared equation. My greatest common factor is a 12x. So I can take a 12 out of each one and I can take an x out of each one. When I take the 12 out, 12 times 3 would give me 36, and 12 times 2 would give me 24. I can set both of these factors equal to 0. Okay, so I set my first factor equal to 0 and my second factor. To solve this first one, I'll divide both sides by 12. And x would equal 0 over 12, which is just 0. For the second one, I'll move the 2 over and divide by 3. So I get the values 0 and 2/3. All right. Well, I know that 2/3 is 0.67. So that might be something useful for us. The next thing we're going to do, now that we have our second derivative, make sure it's the second one. Second derivative, we've set it to 0. We've put them on the number line. We need to choose test points. So I'm going to choose -1 over here. I'm going to choose 0.5 right here. And I'm going to choose, let's say, let's just pick 4. Any number there would work. You could use 1, you could use 2, 3, you could use 1.5, but I'm going to choose 4 today. Now what you have to do with these green numbers is you have to remember where to plug them. We're in the concavity section. So the concavity section says plug these values into the second derivative. And your second derivative is 36x squared minus 24x. Okay, so let's plug in -1. 36 times -1 squared minus 24 times -1. This would be 36 times +1 plus 24. So that's 60, but more importantly, that's a positive 60. Let's plug in 1/2, or 0.5. 36 times 0.5 squared minus 24 times 0.5, or 1/2, however you wanted to write it. This would be 36 times 1/4, or 0.25, which would give me 9. And this would be 24 times 0.5, which would give me 12. So that would be a -3. More importantly, it is negative. So for the last one, I picked 4, a really big number. So when I picked 4, you're going to have 36 times 4 squared. Remember, you're plugging into the second derivative, minus 24 times 4. That's 36 times 16 minus 24 times 4. So this would be 576 minus 96, which is 480, I believe, which is positive. Now remember, the signs here are telling you concavity. Don't draw arrows. We're not on the arrow section. This one's up, this one's up, this one's down. So I am concave up from -infinity to 0, and also from 2/3 to infinity. I am concave down from 0 to 2/3. Now, an inflection point marks any change. So if I look at this particular problem, I see a change at 0, and I also see a change at 2/3. So I have two different inflection points here, and I have to find the y value. Okay, remember, to find the y value, you plug into the original. Okay, so your original function is 3x to the 4th minus 4x cubed plus 6. Let's plug in 0. Zero minus 0 plus 6 would give me 6. You'd have the point 0, 6. Let's plug in the point 2/3. Now, I put this in as a decimal. So you'd have 3 times 0.67 to the 4th minus 4 times 0.67 to the 3rd plus 6. And when you put all of that into your calculator, I think you get something like 5.4. And again, the rounding is not going to be an issue for you, so just round it wherever you'd like within reason. And that's what I would get for that answer. One of the things I want to point out as I'm closing this up is sometimes what looks like a point is actually an interval, and sometimes it's a point. So if you look right here, I have something written as 0 to 2/3. In this particular blank right here, that 0 to 2/3 represents an interval. It is all the points located from 0 to 2/3, all the x values there. In this second blank here, you have 0, 6. That's actually a point. It's a concavity point, or an inflection point, which marks a change in concavity. So even though these two objectives look similar based upon the context in which they're used, one represents an interval and one represents a point. So that's just something I wanted to point out there.